that you can use an advanced method in meshing and use, for example, a proximity. Sizing. I am in the meshing, sizing, and I'm giving them a proximity. And there, I can, for example, tell them that the minimum size should be equal to almost the size of an element. For example, 4 meters. So he cannot put a lot of elements in between. Proximity. So the maximum face size, please use also 4 meters. The maximum size should be, of course, more than 4 meters. You can put, for example, 10 because we don't care, or 100. And you can tell them now to remesh, update your mesh, and you will see now that every bar is one element. You see, it doesn't break into more elements. Every bar is one element. It's like, let's say, the definition of the problem like before. The things now are very easy. You create...
Γιατί το κάνουμε όμως εδώ, γιατί κάνουμε...
Για να είναι το ίδιο το πρόγραμμα με free. Δεν έχει πρόβλημα. Μπορεί να το αφήσεις να σπασμένο σε πολλά elements. Δεν του πειράζει καθόλου. Δεν θα πάρει ούτε χρόνο παραπάνω το πρόγραμμα. Απλώς για να σας εξηγήσω πώς το κάνουμε για να είναι identical to the problem as defined before in our exercise by hand and with the analysis software. It's not a must. It's not a must. And the results will be exactly the same. So we can insert. If somebody would like to have their own weight of the structure, which we didn't have, you can create an acceleration, and due to the standard acceleration, it can create the own weight to idiopathy. We don't need that. Let's have the displacement fixed support. So we have a displacement fixed of the elements of the node, excuse me. In order to choose nodes, please go here to this point. Please write it down in order not to forget it. Vertex. When you do this, he understands here that there is a point. And you can go here and freeze the degrees of freedom. Okay? As I said before, we don't have any movement at... sorry, please tell them here to apply this on the geometry vertex 1. And the x, y, and z direction should be constant.
Sorry. You pressed in order to modify the axis.
Vertex.
Yes.
Για ποιο κέντρο δεν είναι
Μετά το vertex τι έκανατε?
Ναι.
Συγγνώμη. Τι έκαμε τα vertex?
Δεξί κλικ.
Είμαστε στο vertex.
Κάνατε apply.
Πήγατε στο structure, δεξί κλικ, insert, disposal fixed spot.
Είπα πρώτα θέλω να βάλω κάποια displacements, είπα. Να πω πού κινείται ή όχι το σώμα. Τα degrees of freedom δηλαδή. I have to define the degrees of freedom. And here I said we can choose the vertex. It's not chosen here. You choose it, this one.
Πάρα πολύ μεγάλα.
And you have to tell them apply first. And then at each point you go and say it's a constant. there is no displacement, it's only at 0 meters, for example, okay? And in this way, this displacement is created. You see the one I stopped doing before is here, and I actually delete it now. Okay? So I can do this again, insert displacement for the point in here. You see? Apply it, and again, in the x coordinate, it should be free though in this case. Huh? You can move in the x coordinate, and it should be only constant in the y, and in the z coordinate, I just tell them not to move backwards or forwards. Okay? Okay?
Γιατί να κινηθεί σε οποιαδήποτε άλλη κατεύθυνση στη Z, αφού θα του βάλουμε δύναμη στη Z.
Ναι, λέω ότι είναι σταθερό, διότι αν βάλεις μία μικρή δύναμη να σκέψεις να μιλάς το Z και μπορεί να πετάσει για να του πω ότι σε τούτο επίπεδο να μείνεις.
Εσύ, αφού θα ασκείται δύναμη...
Ναι, λέω σου. Εμείς πήγαμε και σχεδιάσαμε πάνω στον πίνακα. Αν μπορούσαμε να σχεδιάσουμε λίγο πιο δεξιά, μπορούσε να μας φύγει το χώρο. Εδώ πρέπει να την πω ότι μιλήσουμε στο επίπεδο του τούτο, οπότε στο Z δεν θέλω να έχει κίνηση. Έτσι. Κατάλαβες, ναι. Ας πω ότι θα πει μια μικρή δύναμη, τουλάχιστον και numerical του προγράμματος, προς τα πάνω, ή να πετάσει ως μια unstable structure. Μείνει στο επίπεδο. Στο Z δεν θα γίνει, αφού έτσι είναι. Αν έχω άλλο τρόπο στον χώρο μετά, δεν θα το κάνω. Εντάξει. Είναι στο Z, δεν θα κινηθώ. There is only a movement of this point on the right.
Αν είχαμε βάλει fix support,
εντάξει, απλώς το έκανα manual για να μην μπορώ να κάνω. Μπορείς να βάλουμε σωστά fix support απευθείας. Πάνω σε ένα σημείο, βέβαια. Απλώς είναι πιο γενικός τρόπος. Έχει διάφορες τρόπους να το κάνεις, βέβαια. Ωραία. Now we can insert the force. Where is the force? Also in a point. In this point, apply. Which is the force? It's, I think it was 2,000 Newton. And which direction was it? It was parallel to this axis, you see, and applied again into the force here. Another time, insert again force. Where? On the vertex here. How much? 5,000 Newton. Which direction? This. It's the direction, huh? It will be exercised here, though, the force, huh? So, okay. So you have the forces. You see them 1, 2 displacement there and there, and you can solve the problem. Here you can give them with right click on the different. Για να λύσεις που τα πας που υπάρχουν. Μπορείς να κάνεις reverse. Sorry, εσύ να κάνεις μια αριστερά, So, you can insert now deformations, for example, or that deformation, or deformations directional, and you can also insert, for example, the axial forces of the beam. You can also have shear forces. Well, okay. These ones are the ones we also determine. Can we have also the stresses in the beams? With the beam tool, I think there are also stresses. Yes, with the beam tool, you have also direct stresses. Right click and choose. Right click in the solution, insert, and choose. Beam tool, it gives us also the stresses. You just tell them here what they have to determine, And with the solve button, it solves the problem. Depending on how many people we are now using the software, it you do the calculations. You now have all the solutions included that you need. Let's have a look at it. Directional deformations. If it helps you to use in millimeters, you can do it with the units in millimeters. So it comes now millimeters with units. So we have a deformation here, maximum deformation, where in the x-axis, that means at this point here, horizontally 0.6 millimeters, and on the other side it's 0 because it's the principal point. If you want to see the deformations in the y direction, vertically, you just choose here y axis, and he wants again a right mouse and evaluates the results again, and now gives you the results in the y direction. It's 1 millimeter, it's around here. Obviously, -1 because it's in the negative direction. Okay? So here is your structure ended, deformed, and the direct stresses, you can see the stresses here. Be careful, the stresses here are averaged. I don't want any other average of stresses. If the one node is 100 Newton and the other one, it would be 60, I don't want an average from 100 to 60. I want the real number of each element. So I don't use the average option in this case. I use a non-average. And with the right mouse click, I evaluate the results again. And you can see now that you have exactly 10 megapascal in this element. The yellow one is between 2 and 4. It's the value you will determine and see in the analysis software. The green one, the light green one, this bar is surely 0, okay? You don't need it actually for this kind of problem. And so on. This bar is -14, is compressed, for example. And then you have the results for each bar on the stresses, and of course on the axial force here. Here are the axial forces. Again, the compression here of -5 kilonewton, 5.6. So these results should be identical to the results of the analysis software. You have to just have a look and compare. I can answer questions now.